On April 13th, 2029, an asteroid will pass closer to Earth than many of the satellites transmitting this video. It already has a name: Apophis. The rock is about 451 meters, which is about 1,480 feet long, longer than the Eiffel Tower laid flat on the ground. It will be traveling at about 26,715 kilometers per hour, which is about 16,600 miles per hour. At that speed, it could cross the continental United States in less than 10 minutes. And when it passes Earth, Apophis will come closer to our planet than many of the satellites carrying GPS signals, weather data, and communications. For millions of people, it will not be an invisible threat buried in a telescope image. It will be visible in the sky. No observatory, no specialized equipment, just a mountain of rock moving across the darkness above you. But the most disturbing part of Apophis was discovered long before the 2029 encounter. In December of 2004, astronomers calculated its early orbit and got a number that changed everything: a 1 in 37 chance of impact, 2.7%. The probability was small, but it was not zero, and the asteroid was not some harmless piece of debris. If Apophis had struck Earth, the impact would have released energy equivalent to approximately 1,200 megatons of TNT. The threat became serious enough that Apophis reached level 4 on the Torino Impact Hazard Scale, the international system used to rank asteroid impact risks. No asteroid before or since has reached a higher rating. Then the calculations improved. More observations arrived. The orbit became clearer. The impact threat was eventually ruled out. Scientists could breathe again, but Apophis is still coming, and its encounter with Earth will do something far more interesting than simply pass by. Earth's gravity will change the asteroid itself, its trajectory, its rotation, its surface, possibly even its internal structure. And three spacecraft from three different countries are preparing to watch what happens. If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. Let's talk about what we actually know. An asteroid is a piece of unfinished history. It formed when the young solar system was assembling, roughly 4.6 billion years ago, from the same raw material that built the planets. Some fragments gathered into worlds, others remained as smaller bodies, preserving ancient rock that never became part of a planet or comet. Most of that material occupies the asteroid belt, a broad region between Mars and Jupiter, containing millions of rocky objects. From a distance, it sounds like a crowded highway. In reality, the bodies are separated by enormous stretches of space. Their paths are governed by gravity, and gravity rarely leaves an orbit completely untouched. Jupiter is especially influential. Its immense mass can disturb an asteroid's trajectory over long periods, while Mars also contributes smaller gravitational nudges. A series of these encounters can gradually move a rock away from a stable region and toward the inner solar system. Some eventually reach paths that cross Earth's orbit. That is where the term near-Earth object becomes useful. It describes a space object whose orbit carries it within 121 million miles of the Sun. The name sounds intimate, but the boundary is vast. Thousands of objects qualify, and most pose no meaningful danger to Earth. A smaller category receives closer attention. A potentially hazardous asteroid is large enough to cause serious regional damage and follows an orbit that can approach Earth's orbital neighborhood. The threshold is roughly 460 feet across, combined with an orbital approach within about 4.65 million miles of Earth's path. Apophis fits both conditions. There is another useful piece of orbital vocabulary. Apophis belongs to the Aten class, a family of asteroids whose paths around the Sun are smaller than Earth's own orbit. Their years are shorter, allowing them to repeatedly move through the inner solar system and encounter Earth's orbital region from unusual angles. For an asteroid as large as Apophis to pass as close as it will in 2029 is exceptionally uncommon. Current estimates place an encounter of this scale and distance at roughly once every 7,500 years. That number stretches beyond ordinary human experience. 7,500 years ago, our ancestors were only beginning to establish permanent agricultural communities in several parts of the world. Entire civilizations have risen and disappeared within a fraction of that interval, yet the next encounter already has a date. April 13th, 2029 is not a prediction waiting for permission from the future. It is an orbital appointment written into the motion of two worlds, calculated years in advance. We can watch the calendar move toward it because the asteroid is already following the path that gravity has given it. And for the first time, you can place that path on a human timetable, with the encounter waiting ahead. June 19th, 2004 began with an ordinary search for moving points of light. At Kitt Peak National Observatory in Arizona, Roy Tucker, David Tholen, and Fabrizio Bernardi were surveying the sky when something unfamiliar crossed their images. The object appeared under difficult circumstances. Its solar elongation was only 56 degrees, placing it relatively close to the sun's apparent position in the sky. Bright glare made observations harder, and the asteroid could easily disappear from view before enough measurements were gathered. For 2 nights, the astronomers collected what they could. Then weather and technical problems interrupted the work. The object received a provisional designation, a temporary catalog label used before an orbit is known well enough for a permanent name. It was recorded as 2004, followed by the letters M and N and the number 4. Then the trail went cold. At that stage, there was no reason to imagine what those few observations would eventually reveal. The measurements simply waited in astronomical archives, incomplete and detached from the larger pattern. Months later, in December, other observations brought the object back into view. Astronomers combined the new positions with the older measurements and began calculating its path around the Sun. Orbital mechanics can turn a handful of observations into a prediction extending years ahead, but only when the measurements agree precisely enough. This time, they did not. On December 21st, the asteroid passed within 8.96 million miles of Earth. That encounter supplied a much longer observational baseline, giving astronomers additional positions from which to calculate its trajectory. Each new position narrowed the range of possible orbits. 6 days later, another piece of the puzzle appeared. Astronomers found older images from March, taken months before the object had been recognized. These are called pre-covery observations, images that were already sitting in archives and can be linked to an object discovered later. Suddenly, the observation arc stretched much farther backward. That extra time mattered enormously. With more positions separated across months, the possible orbital paths became narrower, and the calculation reached farther into the future. The result concerned April 13th, 2029. The preliminary calculation gave Earth a 2.7% probability of impact. For perspective, astronomers generally treat an impact probability above 1 in 10,000 as worthy of serious attention. 2.7% is 270 times that threshold. You can imagine what that number means inside an orbit calculation. The asteroid was no longer simply an unfamiliar point moving through a telescope image. Its measured path had intersected Earth's future position often enough to demand immediate scrutiny, and the date was specific: April 13th, 2029. Numbers like 2.7% are difficult to carry through ordinary conversation. Astronomers needed a language that could translate orbital probability into something the wider world could understand, without turning every uncertain calculation into an alarm. That need led to the Torino Impact Hazard Scale, introduced in 1999. It uses 10 levels, beginning at 0 and rising to 10. 0 indicates no unusual hazard. 10 represents a collision that is certain and capable of causing a global catastrophe. Most newly discovered asteroids remain near the bottom. A preliminary orbit can look concerning for a short time, then disappear from the risk scale as additional observations tighten the calculation. Distance, direction, and timing all become clearer with every measurement. Apophis followed a very different path through that system. On December 27th, 2004, it received a Torino rating of 4. No asteroid had ever reached that level before. None has reached it since. Level 4 describes a close encounter that deserves attention, with at least a 1% probability of an impact capable of producing regional devastation. The number itself matters, but the classification carried another meaning. Scientists were being told that this object had crossed a threshold where continued observation was no longer routine. Across the planetary science community, additional observations were organized rapidly. Telescopes that could contribute useful measurements became important pieces of the same orbital puzzle. Every new position offered another chance to narrow the asteroid's possible future. There was also a second scale operating beneath the public one. The Palermo Technical Impact Hazard Scale is designed for scientists. Instead of assigning an easily understood integer, it compares an asteroid's impact probability with the background probability from all other known objects over the same period. Its values are logarithmic, meaning each step represents a large change in relative risk. Apophis registered above 0 on that scale as well. In practical terms, its calculated threat exceeded the background risk expected from the population of known asteroids during the relevant interval. Then the measurements kept arriving. In January 2005, radar observations added much sharper information about Apophis's position and motion. Radar can measure an asteroid's distance and movement with extraordinary precision, giving orbit calculations a different kind of evidence than optical images alone. The predicted 2029 impact probability began collapsing as those measurements accumulated. A path that had once intersected Earth's future position was gradually pushed away by better mathematics and better observations. The Torino rating eventually fell. The immediate danger was removed, but the same calculations that eliminated the collision also revealed another possibility. Earth's gravity would matter during the close approach, and the exact location of Apophis as it passed could influence where its orbit carried it afterward. The threat had changed shape, and the scientists now had to examine what a near miss could create. Once the direct collision had been removed from the calculations, another question remained. Where would Apophis go after Earth had bent its path? Orbital mechanics allows gravity to create remarkably narrow gateways. Scientists call one a gravitational keyhole, a small region of space where an asteroid's position during a close encounter determines its later trajectory. Pass through the right place, and Earth's gravity can transform a harmless flyby into the setup for a future impact. For Apophis, one of the most important keyholes was only about 1,970 feet wide. That is a remarkably narrow target compared with the enormous distance surrounding Earth. The asteroid would have to cross that particular region during its 2029 encounter for the gravitational geometry to line up correctly. If it did, the altered orbit could bring Apophis back toward Earth on April 13th, 2036. The date fell exactly 7 years after the original close approach, creating a strange symmetry in the orbital calculations. Imagine missing Earth by a vast distance, yet passing through a region only a fraction of a mile wide. Gravity would do the rest. The danger was measured against events already written into Earth's history. An Apophis impact would release energy on a scale comparable to the enormous volcanic eruption of Krakatoa in 1883, except concentrated into a single impact event. The comparison becomes clearer beside smaller objects. The Chelyabinsk meteor of 2013 was estimated at roughly 65 feet across. It exploded high above Russia and injured about 1,500 people, largely through shattered glass. Apophis is vastly larger. The object responsible for the Tunguska explosion in 1908 was estimated at roughly 150 to 200 feet wide. Its atmospheric blast flattened about 830 square miles of Siberian forest. Those events show how much damage relatively modest space rocks can produce. Apophis occupies an entirely different size range. For roughly 2 years, from 2004 into 2006, the possibility of the 2036 keyhole kept Apophis at Torino Level 1. That rating indicated a serious enough possibility to justify continued observation, even as the probability remained uncertain. More observations gradually narrowed the orbit. By 2008, the 2036 keyhole had been eliminated from the calculations. The asteroid was no longer expected to strike Earth on that return. Yet, orbital uncertainty can have several branches. A different gravitational keyhole could still connect Apophis with a later encounter in 2068, and that possibility remained in scientific risk assessments for years. You can see why precision mattered so much. A tiny difference in the asteroid's position during one close approach could determine where gravity sends it decades later. The mathematics was becoming clearer, but Apophis still carried another subtle force into the calculation. Sunlight can move an asteroid even when nothing appears to push it. Every surface exposed to sunlight absorbs energy, warms, and later releases that energy as infrared radiation. Because an asteroid rotates, the heat does not leave evenly from every side. That imbalance creates a minute recoil. The effect is called the Yarkovsky effect, named after the Polish civil engineer Ivan Yarkovsky, who described the principle in the early 20th century. Think of it as a microscopic thrust produced by sunlight itself. The force is extraordinarily small, yet space gives small forces time to accumulate. Over decades, then centuries, a persistent thermal push can shift an asteroid's orbit by measurable distances. For Apophis, those distances mattered. A difference of only a few miles in a predicted future position can determine whether an asteroid passes on one side of a gravitational keyhole or the other. That made the Yarkovsky effect part of the central problem surrounding the asteroid's long-term trajectory. Scientists could calculate the effect in principle. Measuring its actual strength on Apophis was harder. The asteroid's size, rotation, surface properties, and thermal behavior all influence how much sunlight becomes orbital drift. Until that drift could be measured directly, predictions carried an additional layer of uncertainty. The uncertainty affected the expected location of Apophis during the 2029 encounter, which affected calculations for later returns. The distinction was subtle, The asteroid could be completely safe under one trajectory, while a slightly different trajectory might pass through a future keyhole. The difference could emerge from a force too small to notice from Earth. Then radar gave astronomers a much sharper view. In March 2021, the Goldstone Deep Space Communications Complex in California and the Green Bank Observatory in West Virginia worked together on an intensive radar campaign. They repeatedly measured Apophis as it moved through space, building an exceptionally precise record of its position and motion. The new observations transformed the orbit calculation, where earlier projections could carry uncertainties spanning hundreds of miles. The expected 2029 position was narrowed to only a few miles. The Yarkovsky drift could finally be measured directly. That measurement mattered beyond one number. It removed a major source of uncertainty from the long-term orbital model, allowing scientists to determine how the thermal force had been gradually moving Apophis through space. On March 26, 2021, the European Space Agency removed Apophis from its official risk list. The National Aeronautics and Space Administration confirmed that no impact with Earth was expected for at least the next 100 years. The mathematics had reached a remarkable level of precision. Apophis was no longer an unknown trajectory surrounded by dangerous possibilities. Its orbit could be followed with extraordinary confidence. Yet the asteroid was still approaching Earth in 2029. The difference was that scientists could now study the encounter as a precisely measurable event, down to the subtle forces that had once been hidden inside the uncertainty. The shape of Apophis begins to emerge when radar returns are assembled into a three-dimensional picture. What appears from Earth as a moving point becomes something far stranger, an elongated body with dimensions that refuse to fit the image of a typical asteroid. Its average diameter is roughly 1,115 feet, yet its longest axis reaches at least 1,480 feet. Across its shorter direction, the body measures approximately 560 feet. Those proportions give Apophis a stretched appearance, and radar observations suggest an even more distinctive structure. Two broad lobes may be joined by a narrower central region, giving the asteroid a shape often compared with a peanut. Scientists call this arrangement bilobed. It can form when two separate bodies collide at relatively low speed, allowing them to settle together under their mutual gravity rather than breaking apart completely. Such objects are known as contact binaries. Their existence preserves a record of collisions that occurred during the solar system's earliest eras. Apophis may therefore be less like a single carved stone and more like two ancient bodies that became permanently joined. Its surface adds another layer of complexity. Spectroscopic observations place Apophis within the SQ class, a category of stony asteroids whose surface characteristics fall between more weathered S-type material and fresher Q-type material. The distinction reflects how solar radiation and countless small impacts gradually alter exposed rock. Beneath that surface, the structure may be even less orderly. Apophis is believed to be a rubble pile, meaning its interior could consist of countless rocks and fragments held together mainly by gravity. There may be no single continuous mass strong enough to behave like a conventional solid boulder. You can picture the difference in simple terms. A solid rock can transmit force through its structure. A gravitationally bound collection of fragments can shift, settle, and redistribute that force internally. That changes how an asteroid responds to its surroundings. Impacts can be absorbed through movement between individual pieces, while external gravity can rearrange loose material across the surface. The same structure also affects how the body spins and how its mass is distributed. Yet, our picture remains incomplete. No spacecraft has visited Apophis so far. Radar can reveal its outline and provide information about its dimensions, but it cannot show every ridge, boulder, depression, or internal cavity. The outermost layer is expected to contain regolith, a blanket of dust, gravel, and broken rock produced by billions of years of impacts from tiny particles. Some of those fragments may have remained exposed for immense periods, while others could be buried beneath newer material. So when we look at Apophis, we are seeing more than an ancient rock. We are seeing a body whose shape, surface, and internal structure are still being reconstructed from distant measurements, with every observation adding another piece to its physical identity. Apophis completes one journey around the Sun in about 324 days. Earth's own journey takes about 365 days, so Apophis gains ground slowly, returning to the same broad neighborhood at intervals governed by orbital geometry. That difference in orbital period gives the asteroid a distinctive rhythm. Each year, its position relative to Earth changes, and gravitational encounters can alter that pattern over long stretches of time. We can think of the two orbits as paths that repeatedly approach one another, though their exact meeting points shift from one encounter to the next. Rotation adds another layer. Apophis does not spin like a perfectly balanced wheel. Its body tumbles through space, turning around more than one axis at once. This motion is called non-principal axis rotation, a state in which the asteroid's orientation changes through a combination of spinning and wobbling. The main rotation takes roughly 30.4 hours. A secondary motion is superimposed on that spin, causing the asteroid's orientation to wander through space rather than maintaining one fixed direction. For you standing beside such an object, the motion would be difficult to imagine. There would be no single face that always pointed outward, no stable top and bottom, and no simple rhythm repeating from one turn to the next. Astronomers call this tumbling rotation. It can develop after collisions or close gravitational encounters when an asteroid receives enough torque to disturb its previous rotational state. Apophis may have acquired its present motion during a planetary encounter long before humans began measuring the heavens. Rotation also tells us something about the asteroid's interior. A body's response to torque depends partly on how its mass is distributed, so changes in its orientation can provide clues about hidden structure. Then Earth enters the calculation directly. During the 2029 encounter, Earth's gravity will exert a changing pull across the entire asteroid. That interaction can alter both the speed of its rotation and the direction of its rotational axis. Current models suggest the change could be substantial. The spin rate may slow to roughly half its present value or increase to roughly twice its current rate. Its rotational pull could also shift by 10 degrees or more. Those predictions carry uncertainty because we still do not know exactly how mass is arranged inside Apophis. A loosely bound interior can respond differently from a compact body, making the final rotational change sensitive to details we cannot yet observe directly. The orbital change will be just as important. Earth will bend Apophis's path during the encounter, permanently altering the route it follows around the Sunday. After that passage, the asteroid will occupy a different orbit from the one it follows today. Its timing, orientation, and rotation will all carry evidence of the gravitational encounter, turning a single close approach into a permanent change in the asteroid's motion. 20,000 miles sounds enormous until you place it inside Earth's orbital neighborhood. The Moon averages about 238,855 miles away, leaving Apophis less than one-tenth of that distance during its closest approach. That difference changes the scale completely. From Earth, The asteroid will pass closer than many of the satellites surrounding our planet. Some of the most familiar spacecraft occupy that same region above us. Geosynchronous satellites orbit roughly 22,236 miles above Earth's surface. They carry communications, television signals, weather information, and other services we rarely notice until something fails. Apophis will pass inside that orbital band, slipping beneath the altitude of those satellites. The International Space Station is much closer still, orbiting at roughly 250 miles. Its crew will remain far below the asteroid's path, with no danger from the encounter. Distance becomes easier to imagine when we translate it into motion. If you could drive continuously at 60 miles per hour, covering 20,000 miles would require more than 330 hours. That is almost 14 days without stopping. Apophis will cover that distance much faster, moving at roughly 16,600 miles per hour relative to Earth. It could cross 20,000 miles in a little over an hour. And unlike most distant asteroids, its motion will become visible to human eyes. As Apophis approaches its brightest point, it will sweep across the sky at a rate exceeding the apparent width of the full moon each minute. Its brightness is expected to reach approximately magnitude 3.4, placing it within naked eye visibility from suitable locations. You will not need a telescope to detect it. The stars behind it will provide the reference. Watch through binoculars, and the movement should become much easier to recognize as the asteroid changes position against the background from moment to moment. For observers, this creates an unusual experience. A point of light that appears stellar will behave differently, sliding across the sky while the stars around it seem fixed. The scale of the encounter becomes even stranger when we remember what is moving through that space. Apophis is not a small fragment drifting harmlessly past the upper atmosphere. It is a massive asteroid crossing a region occupied by some of humanity's most important orbital infrastructure. Yet those satellites are not its destination. Earth is simply bending its path as the asteroid passes through our gravitational neighborhood. For you watching from the ground, the event will arrive as a moving point of light. Above you, something enormous will be crossing a distance that takes a car nearly 2 weeks to traverse, completing the same journey in a little more than an hour. The view of Apophis will belong mostly to the Eastern Hemisphere. Its path across the sky will favor observers in Australia, Southern Asia, Southern Europe, Africa, and parts of the Middle East, where the asteroid will be above the horizon during the most favorable hours. For those watching from the right locations, April 13th, 2029 will bring an unusual celestial performance. The closest approach will occur during the evening in the regions positioned beneath its path, when Apophis reaches its greatest apparent brightness and its fastest apparent motion. You will not see a blazing object. Instead, Apophis will appear as a moving point of light against the stars. Its apparent motion will be so rapid that long exposure photographs will record a streak, tracing its path across the background sky while the stars remain sharp around it. That movement creates an unusual challenge for photographers. A distant star can remain nearly fixed during an exposure, but Apophis will change position noticeably within minutes. Cameras tracking the stars may therefore record the asteroid as a thin line rather than a point. The experience will depend strongly on where you stand. Across much of North America, the geometry of the encounter will make direct observation far more difficult. During closest approach, Apophis will be below the horizon for much of the continent, leaving observers there with a less favorable view than people farther east. For children alive today, the date carries another dimension. A child born in 2020 will be 9 years old when Apophis passes Earth. Many of those children will be entering adolescence or adulthood during the years when the event becomes part of ordinary school lessons and public astronomy. Amateur astronomers are already considering how to follow the encounter. Telescopes, cameras, timing systems, and coordinated observations can turn a moving point of light into a carefully documented scientific measurement. Schools can participate too. The event offers students something unusual in astronomy, a future celestial event that can be calculated years ahead and then watched as the prediction becomes reality. Humanity has witnessed large objects pass near Earth before. What changes with Apophis is the preparation surrounding the encounter. We know the asteroid's identity. We know its approximate path. We have decades to refine its position, prepare instruments, coordinate observations, and send spacecraft toward it. Earlier, close approaches often arrived without such knowledge. Some objects appeared only after entering Earth's atmosphere, while others passed through space long before humans possessed telescopes, radar, or orbital computers. Apophis therefore occupies a peculiar place in our history. The asteroid will make its passage according to the same gravitational laws that governed every previous encounter, yet this time we will already be waiting. Across thousands of miles, people will look toward the same moving object from different horizons, watching ancient rock cross a sky we have learned to measure. There is a strange way to measure history. Find the moments when something from space came unusually close, then ask how many generations stood beneath it. For Apophis, the record is remarkably sparse. No confirmed asteroid of comparable size is known to have passed this close to Earth during recorded human history. The 2029 encounter is expected to be the closest approach of an asteroid this large that humanity has known about in advance. That distinction matters. We have witnessed smaller objects pass much nearer, and larger objects have certainly crossed Earth's neighborhood over geological time. But Apophis combines size and proximity in a way modern astronomy has never documented before. The best estimates suggest an encounter of this scale occurs roughly once every 7,500 years. That interval is longer than the entire span of recorded civilization. 7,500 years ago, farming communities were beginning to reshape landscapes across the Middle East. The wheel had not yet appeared, and the pyramids of Giza were still thousands of years in the future. Human memory does not stretch that far. Other asteroids help reveal the difference. In 2004, an asteroid designated 2004, followed by the letters EF and H, passed within 26,500 miles of Earth. That sounds remarkably close, but the object was only about 100 feet across. Then came another useful comparison. In June 2024, Asteroid 2024, followed by the letters M and K, passed within about 184,000 miles of Earth. Its estimated width was roughly 500 feet, making it substantial by near-Earth standards. Yet that encounter occurred around 9 times farther away than Apophis will pass. The Chelyabinsk impactor provides an even sharper contrast. In 2013, an object roughly 65 feet wide entered Earth's atmosphere without being detected beforehand. Its arrival injured about 1,500 people and damaged thousands of buildings. Apophis is vastly larger, and its approach has been followed for decades. That difference between warning and surprise changes the meaning of the event. With Chelyabinsk, people looked up only after the sky had already changed. With Apophis, we have watched the calculations mature year after year, refining the expected encounter long before it arrives. There is also something unusual about the timescale. A person alive today can be present for the approach, observe it, record it, and compare the measurements with predictions made decades earlier. You do not need to inherit this event through history books. You can witness it within one human lifetime. For modern astronomy, that makes the 2029 passage more than another close approach. It becomes a rare opportunity to observe a large asteroid at an extraordinary distance from Earth, with instruments ready before the encounter and billions of human eyes capable of following it from the ground. Earth's gravity reaches across space, but its pull will not be identical across Apophis. The side facing Earth will feel a slightly stronger attraction than the far side, creating a difference known as tidal force. We see the same principle on our own planet. Ocean tides respond to differences in the moon's gravitational pull across Earth. During the 2029 encounter, Apophis will experience that effect across its much smaller body, with consequences written directly onto its surface. The asteroid's structure makes the response especially interesting. A rubble pile has no single solid framework holding every piece rigidly together. Instead, countless rocks and fragments are bound primarily by gravity, leaving room for individual pieces to shift when outside forces disturb the whole body. As Apophis approaches its closest point, tidal forces will stretch and compress the asteroid. Slopes that have remained stable for ages could become unstable. Loose material may move downhill, while larger boulders could roll into new positions. Some craters may slump. Dust and gravel can also migrate across the surface. If material moves away from a previously covered area, fresher rock beneath the weathered exterior could become exposed. That fresh material matters because its chemistry has experienced less direct alteration from the space environment. The changes may be subtle from a distance, yet spacecraft instruments should be capable of detecting them. Cameras can compare surface features before and after the encounter, while thermal and spectral measurements can search for changes in exposed material. Gravity will also reach into Apophis's rotation. The same encounter that shifts loose surface material will apply torque to the entire asteroid. Torque is a twisting force that can alter how an object rotates, and Apophis already tumbles through space in a complicated motion. Its response depends partly on how mass is distributed inside. A dense concentration in one region would react differently from a more evenly distributed interior, so the final change in rotation can reveal information that cannot be obtained from surface images alone. The most active period should be concentrated around closest approach. Scientists expect the strongest tidal effects during a window lasting only a few hours, when Earth's gravitational influence changes most rapidly across Apophis. That timing matters for observation. Instruments must already be positioned and operating when the important changes occur, because surface movement cannot be reconstructed perfectly after the fact. When Apophis finally moves away from Earth, its physical state will carry evidence of the encounter. Its surface may contain newly exposed terrain, displaced rocks, and altered slopes. Its rotation will have changed, and its solar orbit will have been permanently redirected. For a few hours, Earth will act as a natural experiment. We will not need to create the force ourselves. Gravity will provide it, and Apophis will record the result. By the time Apophis reaches Earth, several spacecraft will already be waiting for it. Each has a different role, giving us several independent ways to watch the same gravitational encounter unfold. The first is the origins, spectral interpretation, resource identification, and security, Apophis Explorer spacecraft, operated by the National Aeronautics and Space Administration. It began life as the origins, spectral interpretation, resource identification, and security. Regolith Explorer mission, which visited Bennu and returned asteroid material to Earth in 2023. Its journey continues. After the sample capsule separated, the spacecraft was redirected toward Apophis. It will arrive shortly after the close approach, then spend about 18 months studying the altered asteroid from nearby. Its cameras, spectrometers, and laser altimeter will map the surface and measure its changing physical properties. One experiment will take an especially direct approach. The spacecraft thruster investigation of regolith will use the spacecraft's thrusters to disturb loose surface material, exposing layers that normally remain buried beneath the regolith. Scientists can then examine how the material behaves and what it reveals about the asteroid's surface strength. A second spacecraft is designed to witness the encounter itself. The rapid Apophis mission for space safety will rendezvous with Apophis before its Earth flyby and accompany it through the closest approach. Its instruments will observe changes in shape, rotation, surface structure, and other properties while Earth's gravity acts upon the asteroid. Alongside the main spacecraft, two miniature spacecraft will extend the mission's reach. One, named Don Quixote, is being prepared to land directly on Apophis and carry a seismometer capable of measuring vibrations within the asteroid during the encounter. The other, named Farinella, will investigate the surrounding environment with instruments including ground-penetrating radar and a dust analyzer. Then there is Japan's demonstration and experiment of space technology for interplanetary voyage, Phaethon flyby, and dust science mission. Under its revised trajectory, this spacecraft is planned to fly past Apophis before continuing toward its primary destination, the asteroid Phaethon. Its Apophis encounter is planned for before the close approach in April 2029, so Apophis will have observers arriving from several directions, each carrying different instruments and answering different questions. One spacecraft will study the aftermath. Another will watch the gravitational encounter as it happens. A third will make its own close observation during the approach. For us, this changes the meaning of the flyby. Earth will provide the gravity, Apophis will provide the material, and a small fleet of machines will record what happens when the two meet. For all the instruments gathering around Apophis, one question sits deeper than its surface. What is actually holding this asteroid together? We can estimate its mass and outline from afar, yet those measurements cannot reveal how densely its rocks are packed. If Apophis is a rubble pile, gaps may separate countless fragments beneath the visible surface. The encounter with Earth offers a rare test that we can observe directly. Tidal forces will stress the body, and the amount of movement can reveal how strongly its interior resists being reshaped. Then there is the asteroid's strange outline. Radar has suggested two lobes joined around a narrower region, but a radar silhouette cannot capture every contour. Cameras aboard the visiting spacecraft will measure the shape directly, mapping ridges, depressions, boulders, and slopes that remained hidden from Earth. With that geometry established, scientists can calculate how Earth's gravity acts across different parts of the asteroid. Rotation provides another window inward. Apophis does not rotate like a simple top, and its tumbling motion already hints at a complicated history. During the encounter, Earth's gravity will exert torque across the irregular body. Watch how the spin changes, and you gain information about where mass is concentrated. A dense region buried beneath one lobe could influence the motion differently from a more porous interior. Surface material carries another record. For billions of years, sunlight, solar wind, and tiny impacts have altered the exposed layers. This process, called space weathering, can darken and chemically transform asteroid material over immense spans of time. Beneath that altered exterior may lie older material preserved from the early solar system. If landslides or shifting regolith expose fresh layers, instruments can examine their reflected and emitted light. The resulting spectra, patterns within that light, can reveal minerals and chemical components that surface weathering has obscured. A patch of newly exposed ground could therefore become a direct sample of Apophis's ancient composition, even without drilling into it. There is also a larger question. Every asteroid that passes close to Earth experiences some gravitational alteration, whether anyone is watching or not. By measuring Apophis before, during, and after its encounter, scientists can connect changes in its physical state with changes in its trajectory. That connection matters for planetary defense, where a few measurements can change how confidently we model an approaching object. If we understand how irregular, loosely bound asteroids respond to Earth's gravity, future calculations can become more reliable when another object approaches. For you watching from Earth, these measurements may seem impossibly distant, yet each one brings the hidden structure of Apophis into sharper scientific focus. Apophis therefore becomes more than a single asteroid under observation. It becomes a physical test of how small worlds are built, how they move, and how gravity can reshape them. Planetary defense begins long before an asteroid reaches the neighborhood of Earth. The most important advantage is time, because a small change in motion can accumulate into an enormous difference across millions of miles. We have already demonstrated one method. In 2022, the Double Asteroid Redirection Test spacecraft deliberately struck the asteroid moonlet Dimorphos. Its impact shortened Dimorphos's orbital period around its companion by about 33 minutes, proving that a spacecraft can intentionally alter the motion of a celestial body. Apophis presents a harder problem. Its much larger size and probable rubble pile structure could absorb and redistribute impact energy differently. A spacecraft striking loose material may produce a cloud of debris, with some of that material escaping into space and adding recoil to the asteroid. How much momentum transfers depends on the asteroid's structure, shape, and response. The simplest strategy remains the kinetic impactor. A spacecraft would collide with the asteroid and change its velocity by a tiny amount. Given enough warning, even a change too small to notice from Earth could shift the asteroid thousands of miles by the time it reaches a critical point in its orbit. Another possibility is the gravity tractor. A spacecraft would hover near the asteroid for months or years, allowing their mutual gravitational attraction to produce an extremely gradual change in trajectory. There would be no collision. The spacecraft itself would become the source of the steering force. A third concept is a nuclear standoff detonation positioned near an incoming asteroid rather than directly striking it. The intense energy could vaporize part of the surface, producing expanding material that acts like a brief propulsion system. This remains a theoretical option, reserved for circumstances where other methods might not provide enough deflection. Apophis shows why these ideas must be considered years ahead of time. During the years surrounding its discovery, scientists studied how an extremely small velocity change could alter its position before the 2029 encounter. A nudge applied early could move an asteroid away from a gravitational keyhole long before the threat became immediate. That principle changes the entire character of planetary defense. We do not need to overpower an asteroid. We need to influence its trajectory early enough for celestial mechanics to amplify the difference. The double asteroid redirection test gave humanity its first practical demonstration. Apophis gives scientists a different opportunity, allowing them to study how a large, irregular asteroid responds to Earth's gravity with years of preparation and exceptionally precise tracking. For you, the lesson is almost mathematical in its simplicity. Time turns tiny interventions into enormous changes. The earlier we recognize a threat, the more choices remain available, and the less force each choice requires. For much of modern history, dangerous objects could cross Earth's neighborhood without leaving a trace until they were already above us. The Chelyabinsk meteor demonstrated that weakness on February 15th, 2013. A roughly 65-foot object entered the atmosphere over Russia after approaching from near the direction of the sun, where ground-based surveys had difficulty detecting it. No warning reached the people below. Then the atmosphere turned the incoming rock into an expanding burst of energy. Windows shattered across the region, injuring about 1,500 people, while thousands of buildings suffered damage. The event was captured by dashboard cameras, security systems, and mobile phones, giving scientists an unusually detailed record of an atmospheric impact. Yet that same morning contained another near-Earth encounter. Asteroid 2012 DA 14 passed within about 17,200 miles of Earth, only hours after the Chelyabinsk event. The two objects were unrelated. Their coincidence was simply a reminder that several pieces of the near-Earth population can occupy our neighborhood at once. Another milestone arrived in 2008 when a small asteroid called 2008 TC3 was discovered roughly 19 hours before entering Earth's atmosphere above Sudan. At about 13 feet across, it was far smaller than Apophis, and it broke apart harmlessly. Even so, the detection marked a turning point because astronomers had identified an impacting object before it reached the atmosphere. Go back further, and the warning disappears entirely. In 1908, something exploded above the forests of Tunguska in Siberia. Scientists now believe the object was probably an asteroid or comet fragment between 150 and 200 feet wide. The resulting airburst flattened roughly 830 square miles of forest. No telescope announced its arrival. No orbital calculation offered an advance notice. People simply experienced the aftermath. Then came 2019, when an asteroid known as 2019 OK passed within about 43,500 miles of Earth. It was roughly 330 feet wide, yet astronomers found it only about a day before the encounter. Compared with Apophis, it was much smaller, but the warning window was dramatically shorter. Each event exposes a different weakness. Some objects approach from directions obscured by sunlight. Others are simply too small and faint to notice until they are close. And some remain undiscovered because the search itself covers an enormous volume of sky. Our surveys have improved enormously, with automated telescopes scanning the heavens every night. Still, detection depends on where an object is, how reflective its surface happens to be, and whether sunlight hides it from view. Apophis is unusual for another reason. We have been tracking it for decades, refining its path long before the encounter arrives. For once, humanity has time to watch the approach develop in detail, instead of learning about an asteroid only after it has already crossed the sky. The asteroid belt is a reservoir that has been reshaping Earth's neighborhood for billions of years. Between the orbits of Mars and Jupiter, countless rocky bodies continue circling the sun, remnants of a world that never became a planet. Among the larger objects, scientists estimate roughly 1.1 to 1.9 million asteroids exceed 1 kilometer in diameter. Far more remain below that threshold. Most will never approach Earth. Yet gravity continually rearranges the population. Jupiter plays an especially important role. Its enormous mass can redirect passing objects, sometimes pushing comets away from the inner solar system while disturbing asteroids onto new paths. The same gravitational influence can protect Earth in one circumstance and increase exposure in another. Inside the asteroid belt are regions where orbital motion becomes especially complicated. These are called Kirkwood gaps, zones where repeated gravitational interactions with Jupiter prevent asteroids from remaining in stable orbits. An asteroid drifting into one of these resonances can receive a series of gravitational nudges that gradually reshape its trajectory. The 3-to-1 Kirkwood resonance is especially important to the story of Apophis. An asteroid caught there can complete 3 trips around the Sun for every one orbit completed by Jupiter. Repeated gravitational encounters gradually amplify small changes until an object can leave the main belt entirely. Apophis appears to have followed such a path. Over millions of years, gravitational interactions moved it from the asteroid belt toward an orbit that crosses Earth's neighborhood. The process is extraordinarily slow on a human timescale, yet persistent across geological ages. That means the near Earth asteroid population is continually replenished. Objects are being removed from Earth crossing orbits, while others are being delivered into them. The population behaves less like a fixed collection and more like a constantly changing stream. As of 2026, roughly 2,500 asteroids are formally classified as potentially hazardous asteroids. That number represents objects meeting specific criteria for size and orbital proximity, rather than a prediction that they will strike Earth. Most remain far from any collision. Their trajectories can be calculated, refined, and monitored for generations. Still, the source population is enormous. For every asteroid whose orbit becomes familiar to us, countless smaller bodies remain difficult to detect, especially when their positions place them near the Sun from Earth's perspective. You can think of the asteroid belt as an ancient reservoir governed by gravity. Jupiter stirs it. Resonances open pathways through it. Over immense spans of time, some fragments drift inward. Apophis is one result of that process. Removing one asteroid changes almost nothing about the larger population because the gravitational machinery that supplies Earth's neighborhood continues operating. The belt remains, and its rocks continue moving. Apophis carries a record far older than any human archive. Its material formed roughly 4.6 billion years ago, when the young sun was still surrounded by the disk of dust and rock that would become the planets. Nothing about that age is visible from Earth alone, yet the asteroid preserves matter from that earliest era, material that never became part of a larger world. Apophis is therefore less like a broken planet and more like leftover construction material from the solar system itself. For billions of years, that material has traveled through changing conditions. Its surface has endured impacts from tiny particles, repeated heating and cooling, solar radiation, and gravitational encounters with planets. Temperatures across its orbit can range from roughly negative 280 degrees Fahrenheit to positive 200 degrees Fahrenheit. Those extremes gradually alter the outermost layers. This process, called space weathering, changes minerals exposed to sunlight and charged particles, making the surface darker and redder over immense spans of time. From a distance, that weathered exterior can hide what lies underneath. Fresh material may look different. Less altered rock can retain chemical signatures that disappeared from the exposed surface long ago, giving scientists a better sample of the ingredients present when the planets were forming. That distinction matters for Apophis because its surface may not represent the asteroid's original composition. If the 2029 encounter causes landslides or movement of loose material, deeper layers could become exposed for observation. We would then be studying material that has spent almost the entire history of the solar system protected from direct exposure. Its chemistry could preserve clues about the environment surrounding the young Sunday. Other asteroids have already shown why this matters. Samples returned from Bennu and Ryugu contained amino acids, nucleobases, and other carbon-based organic compounds. These substances are important ingredients in chemistry associated with life, although their presence alone does not indicate life existed there. Apophis has never been sampled directly, so we do not yet know whether it carries the same inventory. Spectrometers aboard future spacecraft can examine newly exposed surfaces by measuring how they absorb and reflect different wavelengths of light. Every spectral feature adds another piece to the record. Minerals reveal their structure. Organic compounds leave chemical fingerprints. Water-bearing materials can reveal how volatiles were stored and altered. You can imagine those layers as pages written by sunlight, impacts, and time. The oldest pages may remain buried beneath the surface. If fresh material emerges during the encounter, scientists could compare it with the weathered exterior and reconstruct how the asteroid changed. Apophis would then become more than an object passing through Earth's neighborhood. It would become a surviving fragment of the material from which our planetary system was assembled, carrying chemistry that has remained almost unchanged since the beginning. Some names are chosen long before their meaning becomes clear. Apophis received its official name in 2005 after its discoverers proposed it to the International Astronomical Union's Working Group for Small Body Nomenclature. The name comes from Apep, an ancient Egyptian serpent associated with chaos, darkness, and destruction. Each night, according to Egyptian cosmology, Apep confronted Ra, the sun god, during the journey through the underworld. The struggle was repeated with every sunset. If Ra prevailed, the sun would return with morning. For the astronomers studying this newly discovered object, the symbolism had a practical origin. Apophis had appeared on their screens as a calculation problem with an unsettling possibility attached to it. Its early orbit estimates suggested a measurable chance of collision with Earth. That possibility shaped the name. In December of 2004, observations were arriving from telescopes separated by thousands of miles, and each new measurement changed the predicted path. The asteroid had only recently been discovered, yet its orbital uncertainty was already being examined against the future position of our planet. At one point, the calculated impact probability reached roughly 2.7%. That number was tiny in ordinary life, but extraordinary for an object crossing the Earth's neighborhood. A probability that large demanded attention. 3 astronomers had found the object. They had watched its position shift from one observation to another, then used those movements to estimate its orbit around the Sunday. Every additional observation narrowed the possibilities. Still, the name carried an unusual weight. Apep represented a force that returned again and again, challenging the passage of light through darkness. The comparison fit an asteroid whose orbital mathematics had suddenly become a subject of worldwide attention. You can hear the history inside that name. It belongs to mythology, but it also belongs to a particular moment in modern astronomy when a faint point of light became a problem measured in probabilities. Then the observations continued. Better measurements changed the orbit. The probability fell. Additional radar observations eventually removed the known collision scenarios that had once made Apophis famous. The mathematics kept changing, even as the name remained fixed. Yet the ancient name remained. There is something fitting about that permanence. Scientific knowledge changes as measurements improve, while names can preserve the circumstances that surrounded a discovery. Apophis, therefore, carries two histories at once, one reaching back thousands of years into Egyptian mythology, and another beginning with astronomers watching numbers change on computer screens. The god of chaos became the name of an asteroid. The asteroid became a lesson in how uncertainty works and in how quickly knowledge can change when better observations arrive. And beneath the mythology is something very human. We gave a distant object a name because, for a brief moment, we did not know where its path would lead. By the time Apophis pulls away from Earth on April 14th, 2029, its path through space will already have changed. Earth will have exchanged a small amount of gravitational energy with the asteroid, altering the orbit it follows around the Sunday. Before the encounter, Apophis completes one circuit in roughly 324 days. Afterward, that period will be different because the asteroid will leave Earth traveling along a newly shaped trajectory. The change may be small compared with the vast scale of the solar system, yet even a modest alteration matters when projected across decades. For scientists, the first task after the flyby will be to measure exactly what changed. Radar observations, optical tracking, and spacecraft measurements can establish the asteroid's new position and velocity with far greater precision than before. Those measurements will replace a broad range of possible trajectories with a much narrower orbital solution, giving researchers a stronger foundation for every later calculation of its position and motion. That new solution matters for another reason. The gravitational encounter will also change how Apophis rotates and how heat leaves its surface, potentially altering the tiny thermal force known as the Yarkovsky effect. Because that force accumulates over long periods, a small change in its strength can gradually move the asteroid farther from its predicted position. We therefore cannot treat the post-encounter orbit as a simple extension of the old one. The flyby changes several physical conditions at once, including the trajectory, rotation, and possibly the distribution of material across the surface. This is where the rapid Apophis mission for space safety becomes especially valuable. By observing Apophis before the closest approach, the spacecraft can establish a detailed baseline for its shape, rotation, and physical behavior. Scientists can then compare those measurements with observations made after Earth has passed. Imagine having two photographs of a moving object, separated by a powerful gravitational encounter. The difference between them contains information about the forces that acted in between. With enough measurements, researchers can work backward from those changes and refine the physics governing the asteroid. The post-encounter calculations will therefore become more precise, but they will also become more interesting. A newly measured orbit must account for the asteroid's altered spin and thermal behavior, while continued observations will reveal whether those models match reality. For you, the important distinction is easy to miss. The close approach does not simply end when Apophis recedes from Earth. The encounter becomes part of its orbital history, permanently changing the path that future astronomers will calculate. By the end of the flyby, Apophis will carry a new trajectory shaped by Earth's gravity. Every later prediction will begin from that changed state. A probability can be mathematically small and still demand attention. That contradiction became visible when Apophis briefly carried a measurable chance of striking Earth. 2.7% is difficult to picture. numbers that small rarely have a physical shape in everyday experience. Yet, if you were told your chair had a 2.7% chance of collapsing beneath you, you would probably choose another seat. Asteroid risk creates the same problem on a planetary scale. Most people will never witness a dangerous asteroid approach during their lifetime, while the consequences of a genuine impact could extend across regions or even continents. Our instincts evolved around immediate hazards, not probabilities accumulated across centuries. That mismatch is one reason scientists developed the Torino scale. Created as a communication system for near Earth objects, it translates complicated calculations into levels that describe both likelihood and potential consequences. The goal is straightforward: give the public useful context without turning uncertainty into panic. Apophis briefly reached level 4 on that scale. It became the first real asteroid to test how such a warning would function outside theoretical exercises. Researchers had to exchange observations rapidly, update calculations, explain changing probabilities, and communicate what those numbers actually meant. The scientific response remained measured. Public attention was different. Headlines compressed evolving calculations into simple statements about danger, while the underlying astronomy continued changing with every new observation. Then interest faded. That pattern revealed something important about planetary defense. Finding an asteroid is only the beginning. Scientists also need reliable channels for sharing measurements, coordinating interpretations, and communicating uncertainty across institutions and national boundaries. You can think of the problem as a chain with many links. Telescopes provide observations. Researchers turn those observations into orbital models. Specialized teams assess potential hazards. Agencies coordinate responses. Public institutions explain what has been established and what remains uncertain. A weakness anywhere in that chain can create confusion. The Apophis experience exposed how separated some of these functions could become. Different organizations possess different pieces of information, expertise, and authority. Bringing those pieces together required coordination that had rarely been tested under realistic conditions. The 2029 encounter provides an unusual opportunity because there is no emergency demanding an immediate decision. Scientists can observe the process while having time to compare models, share data, and examine how international teams work together. That preparation matters because a real warning would arrive with uncertainty attached. An asteroid's orbit would initially be represented by a range of possibilities, and each observation would reshape that range. We would need to understand the numbers before deciding what action they justify. That requires scientists, governments, observatories, and communication networks operating from the same evidence. Apophis, therefore, became more than an astronomy problem. It exposed a human one: our ability to recognize a distant risk, understand its probability, and coordinate a response before probability becomes certainty. Finding a dangerous asteroid begins with something almost ordinary: taking pictures of the sky repeatedly. The crucial difference comes from comparing those pictures over time. Across the planet, automated surveys examine enormous numbers of stars, searching for points that shift against the distant background. The Catalina Sky Survey, operated by the University of Arizona, is one of the major programs involved. Panoramic Survey Telescope and Rapid Response System adds another wide-field survey from Hawaii, while the Spacewatch program follows objects that might otherwise escape attention. Then there is the Asteroid Terrestrial Impact Last Alert System, a network designed to scan the sky frequently and identify objects approaching Earth's neighborhood. Each survey contributes observations from different locations, times, and viewing angles. The Vera C. Rubin Observatory is expanding that capability. Its legacy survey of space and time is designed to repeatedly image the southern sky, revealing faint moving objects that previous surveys could miss. Instead of waiting for an asteroid to become obvious, astronomers can build enormous databases of changing positions and let automated software identify unusual motion. Space-based observation adds another advantage. The Near-Earth Object Surveyor is being developed as an infrared space telescope specifically intended to find potentially hazardous asteroids. Infrared instruments can detect heat, allowing astronomers to identify some dark objects that reflect too little visible sunlight for conventional searches. Once an asteroid is discovered, the problem changes. Finding the object is only the first step. Scientists need to determine where it is going. Optical observations provide positions, while radar can measure an asteroid's distance and motion with extraordinary precision. The Goldstone Deep Space Communications Complex and the Green Bank Telescope have played important roles in refining the orbits of near-Earth objects. Those measurements become especially valuable when an asteroid approaches Earth. A few additional observations can dramatically narrow the range of possible trajectories, transforming a broad prediction into a much more precise orbital path. Yet a large gap remains in the census. Scientists estimate that roughly 95% of near-Earth asteroids, larger than about 3,300 feet, have been discovered. For objects between roughly 460 and 3,300 feet, the estimated completeness is closer to 40%. That second population matters enormously. These asteroids are large enough to cause devastating regional or national consequences, yet many remain unidentified. Apophis belongs to that partially known population. We found it in time to study its orbit for decades. But somewhere beyond the current survey limits, other objects are still moving through the darkness, waiting for their paths to cross the fields of our telescopes. The search, therefore, has no final count, because discovery itself changes the map and reveals new regions where additional objects may be hiding. Every newly discovered asteroid improves the map, while every undiscovered one remains outside it. If Apophis were ever placed on an impact course, the ground beneath us would become part of the calculation. The outcome would begin with location. An ocean strike would transfer enormous energy into seawater, launching waves outward from the impact site. The most severe effects would concentrate along nearby coastlines, where incoming water could surge far inland. Depth, shoreline shape, and the asteroid's entry angle would all influence the final wave pattern. There would be no single global tsunami height. Far from the impact point, wave energy would spread and weaken, although exposed coastlines could still face dangerous flooding and powerful currents. A continental impact would unfold differently. At roughly 3 miles across, the resulting crater would scar the landscape on a scale rarely witnessed by humans. Around the impact point, temperatures, pressure, and rapidly expanding debris would destroy structures across a vast region. The atmosphere itself would become part of the event. A pressure wave would race outward at extraordinary speed. Compressed air would strike buildings with enough force to break windows, damage structures, and injure people far beyond the crater. Above the ground, pulverized rock and fragments of the asteroid could rise into the atmosphere, then return across a broad surrounding area as falling ejecta. Some material would remain suspended temporarily, while larger fragments would descend much sooner. The energy involved is difficult to imagine in ordinary terms. Using estimates for Apophis's size and bulk density, scientists place a hypothetical impact in the range of roughly 1,200 megatons of explosive energy. That is about 80,000 times the energy released by the bomb dropped on Hiroshima in 1945. Those numbers describe energy, but they do not describe one uniform zone of destruction. Terrain, geology, atmosphere, impact angle, and the asteroid's internal structure would all change the outcome. A rocky landscape would respond differently from an ocean basin, while mountains and valleys could redirect pressure and debris. Local weather could also influence how airborne material spreads after the initial blast. The closest modern comparison is the Tunguska event of 1908. An object far smaller than Apophis exploded above Siberia, flattening roughly 830 square miles of forest without leaving a conventional impact crater. The explosion was detected through its effects across a huge region. Apophis contains vastly more material, yet even an impact of this scale would not automatically end human civilization. Scientists classify an event of this magnitude as a regional catastrophe rather than a global extinction event. Regional, however, can mean millions of lives. It can mean cities, farmland, infrastructure, and ecosystems transformed across an area comparable to a large country. For you and me, the important distinction is scale. Earth would survive, but the human landscape around the impact would be profoundly rewritten. Earth carries the scars of impacts, even when most have disappeared. Across deep time, erosion has softened craters, oceans have hidden them, and moving continents have erased their outlines. What remains is only a fraction of the record. One of the clearest survivors is Chicxulub, buried beneath Mexico and the Gulf of Mexico. Its impact structure stretches roughly 110 miles across, formed about 66 million years ago. The asteroid itself may have measured 6 to 9 miles wide, many times larger than Apophis. Its arrival reshaped the atmosphere, disrupted food chains, and contributed to the extinction of roughly 75% of species then living on Earth. Far older scars reach across continents. Vredefort in South Africa spans about 190 miles and formed roughly 2 billion years ago. It is the largest confirmed impact structure known on Earth. The Sudbury Basin in Ontario preserves another enormous collision created roughly 1 billion years ago. These places are geological archives where fractured rock and altered minerals preserve evidence of energy released in moments. Some craters have been worn almost beyond recognition, leaving only chemical signatures or unusual rock structures for geologists to find. Yet, impacts have done more than destroy landscapes. Early Earth passed through a period known as the Late Heavy Bombardment, roughly between 4.1 and 3.8 billion years ago, when large impacts were more frequent across the inner solar system. The evidence is especially strong on the Moon, whose cratered surface preserves ancient events that Earth has largely erased. Those collisions may also have helped shape the ingredients available to early life. Asteroids and comets can carry water and organic compounds, delivering material to planetary surfaces during impacts and close encounters. We cannot trace every molecule to one particular collision, but the possibility changes how we understand Earth's early environment. The Moon itself may preserve an even larger chapter. Current models suggest that a planetary body called Theia struck the young Earth about 4.5 billion years ago. Debris thrown into orbit eventually gathered into the Moon. Imagine that. The companion world beside us may be the lasting remnant of a planetary collision. For life, impacts have therefore carried two opposing consequences. They can erase ecosystems within hours, yet they can also alter environments, redistribute chemistry, and create new opportunities for evolution. The collision that ended the age of no-Navian dinosaurs changed which creatures inherited the recovering world. Mammals expanded into ecological spaces that had been occupied for millions of years. Much later, one branch produced us. When we study Apophis, we are therefore studying more than a potential hazard. We are examining one part of the same cosmic process that has repeatedly reshaped Earth, from its earliest days to the world beneath our feet today. When Apophis moves away from Earth after the 2029 encounter, observation will become a permanent part of its story. The asteroid will continue along its path around the Sun, returning to the neighborhood of our planet at intervals shaped by its changing orbit. Another approach comes in 2036, at a substantially greater distance than the remarkable passage in 2029. Further encounters will occur in 2051 and at other points throughout this century. Each one gives astronomers another opportunity to compare a precisely measured orbit against the predictions built from decades of observations. By then, Apophis will occupy an unusual position in planetary science. Radar measurements, spacecraft observations, optical tracking, and measurements of its interior will provide an exceptionally detailed record of one near-Earth asteroid. Every new observation can be compared against that growing archive, allowing scientists to distinguish genuine changes from uncertainties in earlier models. That distinction matters because orbital prediction is an evolving calculation. Tiny forces accumulate over long periods, and even subtle changes can alter where an asteroid appears years later. Solar heating can produce a gradual drift called the Yarkovsky effect, while gravitational encounters with planets can reshape an orbit much more abruptly. With Apophis, researchers will have an unusually rich set of measurements for testing both effects. You can think of each future passage as another entry in a continuously expanding record. Telescopes will measure its position against distant stars, radar can refine its distance and motion, and spacecraft observations will provide physical information that Earth-based instruments cannot obtain alone. The asteroid will become a reference point for comparing prediction with reality. Hundreds of other near-Earth asteroids are monitored through long-term observing programs. Their paths matter too. Yet Apophis combines several qualities rarely found together, including substantial size, repeated accessibility, an exceptionally close known encounter, and an unprecedented concentration of scientific observations. That combination changes what happens after 2029. Instead of fading from attention once the immediate event has passed, Apophis will remain a familiar object in planetary defense research. Its measurements can help researchers test models, improve tracking methods, and understand how close encounters modify asteroids over time. For you, that means the story does not belong to one evening alone. Every future observation adds another point to an orbital record stretching across generations. The asteroid will keep moving, and Earth will keep turning beneath its changing path. Long after the cameras from 2029 have stopped recording, Apophis will still be measured. Its position will be checked, its orbit recalculated, and its physical behavior compared with earlier observations. In that continuing record, we gain something rare in astronomy, an object whose future can be watched, becoming more understandable with every return. An asteroid does not recognize a border. Its trajectory crosses the invisible lines humans draw across maps, while the effects of an impact could spread far beyond the original location. That simple fact makes planetary defense an international responsibility. A threatening object would be tracked from observatories in several countries, its orbit refined through shared measurements, and its risk assessed by scientists working across institutions. No single government could observe every stage alone. The framework for doing this is surprisingly young. During the 1990s, the United Nations Office for Outer Space Affairs helped establish international work on near Earth objects. In 2013, the International Asteroid Warning Network was formally established, creating a system for sharing discoveries, improving orbital calculations, and communicating potential hazards among participating organizations. Its purpose is practical. When a new asteroid appears, observations can be distributed quickly to researchers around the world. Additional measurements can reduce uncertainty in its orbit. If the object presents a meaningful hazard, information can move through an established international warning chain rather than remaining inside one institution. Another body handles the mission planning side. The Space Mission Planning Advisory Group brings together national space agencies to consider what a physical response might require. That could involve reconnaissance, trajectory measurements, or an attempt to alter an asteroid's path. The distinction matters. Finding an asteroid is one problem. Deciding how humanity should respond is another. Apophis gives these systems an unusually useful test. During the 2029 encounter, spacecraft associated with the National Aeronautics and Space Administration, the European Space Agency, and the Japan Aerospace Exploration Agency will contribute observations at different stages of the encounter. Their measurements can be compared, combined, and distributed among researchers studying the same object. 3 agencies, 1 target. The challenge extends beyond spacecraft. Scientists must coordinate observing schedules, exchange measurements, maintain compatible orbital models, and communicate changing results without creating unnecessary confusion. Each organization brings its own instruments, procedures, and responsibilities, yet the asteroid follows one physical trajectory. The encounter also places unusual demands on timing. Measurements collected before, during, and after the passage must remain connected, allowing researchers in different locations to build a consistent record. Even small disagreements in timing or position can matter when scientists are reconstructing a rapidly changing orbital path. The Double Asteroid Redirection Test mission already demonstrated that a spacecraft can deliberately alter an asteroid system's motion. That achievement answered an engineering question. Apophis presents a different one. Can many nations coordinate around the same threat with equal precision? For planetary defense, that may be just as important as the spacecraft themselves. A future warning could arrive with years of preparation, but those years would only matter if observations, decisions, spacecraft, and governments remained connected. The sky has no jurisdiction. Our response cannot depend on one. A child born in the year 2020 will be 9 years old when Apophis crosses Earth's neighborhood in 2029. For that child, the date may become something ordinary, remembered through school lessons, photographs, and a point of light moving across the evening sky. That is where the longer story begins. The generation growing up around this encounter will inherit an asteroid studied with an unusual depth of detail, giving future scientists a reference point for understanding other near-Earth objects. Measurements gathered around the encounter can remain useful long after the spacecraft have finished their work. Imagine being a student decades from now, opening a scientific archive and finding observations recorded during the 2029 passage. You could examine maps of the surface, measurements of its rotation, and detailed records of how Earth altered its trajectory. the asteroid would become more than a distant object in a catalog. It would become a natural laboratory preserved in data. Some of the most valuable information may come from its physical structure. If instruments can measure how vibrations travel through Apophis, researchers can learn how its interior is arranged and how strongly its material holds together. That matters for understanding how asteroids form, break apart, and respond when gravity or spacecraft disturb them. The spacecraft origins, spectral interpretation, resource identification, and security, Apophis Explorer, is also part of this extended scientific record. After completing its original mission around Bennu, the spacecraft was redirected toward Apophis, where it can examine the asteroid's surface and composition after the close approach. It is important to separate that mission from sample return. The spacecraft is not currently designed to bring pieces of Apophis back to Earth. Instead, it can study the exposed surface directly, examine changes caused by the encounter, and compare those observations with what we already know from other asteroids. That distinction still leaves future researchers with something remarkable. We can place laboratory measurements beside spacecraft observations and ask how closely an asteroid, seen from millions of miles away, resembles material examined on Earth. Samples from Ryugu and Bennu have already revealed water-bearing minerals and complex organic compounds, giving scientists new ways to interpret what remote observations can tell us. For children watching Apophis in 2029, the most interesting part may be how much remains useful afterward. Their generation could become the one that turns a single asteroid encounter into decades of comparative research. Some may become astronomers, others may build spacecraft, and some may simply remember looking upward that night. Years later, those memories could sit beside measurements gathered from the same world, connecting a human lifetime with an object that has traveled through space for billions of years. For most of Earth's history, the sky offered no advance notice. A bright object could cross the heavens, disappear beyond the horizon, and leave its consequences behind before any creature could understand what had happened. There was no warning system. No observatory network waited for approaching rocks. No calculation could turn a distant point of light into a prediction measured in years. Life simply encountered whatever the solar system delivered. Apophis belongs to a different chapter. When astronomers identified it in 2004, they could calculate its orbit, compare possible trajectories, and continue refining those calculations as new observations arrived. The process transformed uncertainty into something measurable. That distinction matters. You can prepare for a storm because you know it is coming. An asteroid presents a far greater challenge because its path unfolds across enormous distances and depends on forces too small to notice directly. Yet mathematics allows us to see those forces accumulating over time. Each observation narrows the range of possible futures. Each radar measurement adds another piece of evidence. Each improved model reduces the space in which uncertainty can hide. The asteroid that struck near what is now Mexico 66 million years ago offered none of that opportunity. The object was never tracked from a telescope, its trajectory was never calculated, and no civilization existed with the ability to alter its course. We live under different conditions now. Our species can detect an approaching object before it reaches Earth. We can measure its motion, estimate its physical properties, and compare possible outcomes with observations gathered from other worlds. We can even send machines into deep space to change an asteroid's movement deliberately. That ability remains limited. A warning is useful only when there is enough time to respond, and a response requires technology, coordination, and decisions made before certainty becomes absolute. Still, something fundamental has changed. For the first time, A species on Earth can look outward and recognize a potential danger while it remains far away. We can place that danger on a timeline, study its behavior, and decide whether intervention is necessary. Apophis, therefore, represents more than a particular asteroid. It represents a new relationship between life and the environment beyond Earth. The rocks moving through space are ancient, but our ability to notice them is extraordinarily recent. Think about what that means. You are living during the first era, when humanity can receive advanced knowledge of a natural object capable of causing immense destruction, then use that knowledge to plan a response. Awareness does not promise control. It gives us a choice. That choice begins with observation, grows through understanding, and becomes meaningful only when people are willing to act together. For every civilization that existed before ours, the sky remained something to endure. For us, it has become something we can study, measure, and sometimes influence. Right now, Apophis is moving through another ordinary stretch of its orbit, far from the moment that has made it famous. Nothing about the asteroid's motion responds to our calendars, observatories, or preparations. Gravity continues its work. Its journey around the Sun takes 324 days. During that cycle, its distance from Earth changes continually, while the geometry between the two worlds slowly rearranges itself. We measure those changes with clocks, telescopes, radar observations, and precise mathematical models. For us, the years between encounters can feel enormous. For Apophis, they are brief portions of a much older journey. The asteroid has spent roughly 4.5 billion years moving through a solar system governed by the same forces that guide it today. You might imagine that such an ancient object would follow a perfectly repeating path. In reality, every orbit is slightly different. The gravity of planets alters its motion. Sunlight produces tiny changes over time, and each close planetary encounter can reshape the trajectory that follows. Those effects are extraordinarily small from one moment to the next. Given enough time, they accumulate. This is where human patience becomes part of astronomy. A measurement made today may matter most decades later, when researchers compare it with observations from another passage. A few minutes of improved timing can influence models that extend across generations. Between encounters, there is also work happening on Earth. Observatories continue searching for faint objects, astronomers refine orbital solutions, and tracking networks preserve measurements that might otherwise become scattered across decades of research. The process rarely produces a dramatic image. Its value lies in continuity. Apophis itself offers a particularly useful reference because its future motion can be measured repeatedly under changing conditions. Each return gives scientists another opportunity to compare prediction with observation, testing how accurately gravitational models and subtle physical effects describe a real asteroid. The mathematics can become remarkably sensitive. A tiny difference in position, velocity, or spin can alter the predicted location much farther along the orbit. That is why observations collected at different times are so valuable. They anchor the calculation to reality. For you, the strange part may be how little appears to happen during these intervals. There is no visible countdown written across the sky. No marker announces that another day has passed along the asteroid's ancient route. Yet the trajectory keeps unfolding. Somewhere beyond our immediate surroundings, Apophis continues along its path, carrying the record of countless encounters with sunlight, planets, and the changing architecture of the solar system. We do not need the asteroid to acknowledge our presence for its motion to become part of human knowledge. A telescope records another position. A computer updates another orbit. An astronomer compares another measurement. Then the asteroid keeps moving. That is the rhythm of planetary science: observation followed by calculation, calculation followed by another observation. Across immense spans of time, those small acts allow us to follow something that began its journey long before humanity existed. On the evening of April 13th, 2029, millions of people will have the chance to look upward and notice something unusual. Apophis will appear as a moving point of light, crossing the background stars quickly enough to reveal that it is not another distant sun. Most people may never realize what is passing overhead. For them, it could be one more light among thousands. Yet somewhere nearby, astronomers will be following the same object with instruments built to measure changes far too small for human vision to detect. That difference matters. For the first time, our species can witness a close approach while understanding its cause, its trajectory, and its physical nature. We know where Apophis came from, how its orbit evolved, and how Earth's gravity will alter its path. The knowledge itself becomes part of the encounter. Look up, and you are seeing an ancient object. Look closer, and you are seeing a scientific experiment. Spacecraft will have traveled roughly 93 million miles through interplanetary space to reach the asteroid, carrying instruments designed to examine its surface, motion, and structure. Some measurements will last only for moments, while others may remain useful for generations. The encounter will also leave physical changes behind. Earth's gravity will reshape Apophis's orbit around the Sun, while tidal forces may disturb loose material across its surface. Future observations can compare those changes with the conditions measured before the passage, allowing scientists to test models against the asteroid itself. For you, the strange part is the scale of participation. A person standing beneath the night sky does not need a telescope to become part of the observation. Looking upward connects a human lifetime with an object that began forming billions of years before Earth became a living world. Apophis carries no message for us. It does not recognize the machines approaching it, the antennas tracking its position, or the people calculating its future. Its motion remains governed by gravity, sunlight, and the physical structure of the asteroid itself. Yet our response gives the encounter another dimension. We looked outward. We noticed something moving among the planets. Then we gave it a name, measured its orbit, studied its composition, and built machines capable of meeting it. The solar system remains enormous. We remain very small, but size has never been the measure of understanding. A species can occupy one small world and still develop the ability to study objects across vast distances, predict their motion, and change what happens next. On that April night, Apophis will pass through our planetary neighborhood and continue onward. We will remain here, watching, measuring, and learning from the same ancient object. For once, the sky will not simply happen above us. We will know what we are looking at,